I don't want to turn this into a debate on hydrogen fuel cells because I just think that they're extremely silly. And the people have published, there's multiple sort of rebuttals of it online. It's just very difficult to make hydrogen and store it and use it in a car. Hydrogen is an energy storage mechanism. It's not a source of energy.
Elon Musk finally reveals what may be sitting behind the engine disasters hitting GM, Toyota, Honda, and Hyundai. And the warning is not as complicated as people think. It starts with one uncomfortable truth. The modern gasoline engine is full of parts that have to move perfectly, every second, under heat, pressure, oil, and vibration. And when one small thing goes wrong, the damage does not stay small. That is what makes this so serious. These are not unknown car companies. These are some of the biggest names on the road, trusted by millions of drivers for decades. But now, one after another, major brands are facing engine failures that all seem to point toward the same kind of weakness inside the machine. Musk has been saying for years that the old engine world carries a hidden risk. Too many parts, too many failure points, too many ways for one defect to turn into a disaster. So why are GM, Toyota, Honda, and Hyundai suddenly facing engine problems at this scale? And did Elon Musk just expose the one weakness traditional automakers can no longer hide? Elon Musk built Tesla around one mechanical idea. A gasoline engine depends on hundreds of moving parts, while an electric motor uses far fewer. Tesla's own material lists what disappears: engine oil, filters, spark plugs, crankshafts, rods, and valves. It describes the electric motor as mechanically simpler. That is why Elon Musk, Tesla, 4 brands, and one warning now meet. GM's problem made that warning hard to ignore. The company recalled 597,630 vehicles with the 6.2-litre L87 V8 after rod and crankshaft defects were linked to engine damage and sudden power loss. The list included Escalade, Silverado, Tahoe, Sierra, and Yukon models built between March 2021 and May 2024, turning one internal defect into a massive public recall. Toyota faced a similar chain inside its V35A twin-turbo V6. Machining debris could reach the crankshaft bearings and begin wearing them down. Toyota recalled 102,092 vehicles in May 2024, added 126,691 more in November 2025, then recalled another 43,566 Tundras in May 2026 after later engines showed the same bearing damage again under normal road use. Honda's failure began with crank pins ground into the wrong shape. That mistake could wear the connecting rod bearings until they seized. Honda recalled 248,999 vehicles, but the trouble did not stop there. NHTSA later opened PE 25008, covering about 1,410,806 vehicles, after 3,012 incidents appeared around the same part of the engine and raised a much wider concern. Hyundai had already shown how the same damage could end. Metal debris inside Theta 2 oil passages could slow lubrication, raise bearing heat, create knocking, and finally stop the engine. NHTSA later said delayed recalls covered more than 1.6 million vehicles and led to $210 million in penalties. Across Hyundai, Kia, and 4 manufacturers, the path looked nearly the same. Tiny defects could travel until the whole engine failed. The failure begins long before the driver hears it. A tiny piece of metal can remain inside an oil passage. A crankshaft can leave the factory slightly out of shape. A rod bolt can sit below its proper setting. For GM, Toyota, and Hyundai, the engine may still sound normal while damage has already started deep inside the block. Every few seconds, the crankshaft turns thousands of times. The connecting rods carry the force of each combustion cycle, and thin bearings keep the metal from grinding against itself. Everything depends on shape, pressure, and clean oil. The crankshaft, connecting rods, bearings, and oil film must keep working together without a break. Once debris blocks that flow, the balance begins to disappear. Oil stops reaching the bearing properly. Friction rises. Heat builds. Metal starts wearing away. Hyundai's Theta 2 filing followed that same path from restricted flow to early bearing damage. The knock comes later. By then, Theta 2, NHTSA, friction and heat are already part of the same failure. The first sound is often a metallic knock. It grows faster as the engine speeds up because the damaged rod is no longer moving smoothly around the crankshaft. Then other signs begin to appear: rough running, hesitation, smoke, reduced power, or an oil pressure light. Knocking, smoke, warning lights, and power loss arrive only after the damage has spread. The final moment can come without much warning. A bearing can seize, a rod can break, the engine block can split, oil can escape, and the vehicle can lose power at highway speed. That is why the filings connect these failures to crash and fire risks. Across GM, Toyota, Honda, and Hyundai, different engines were reaching the same end through almost the same hidden path before the driver has time to react safely. By January 16, 2025, GM could no longer treat the failures as scattered complaints. The company opened a new review of its 6.2-liter E87 V8. Even though similar work had already been closed in February 2022, June 2023, and July 2024. The engines kept failing, and the growing field record made another look impossible to avoid inside vehicles already sold. Once the engines came apart, the problem became easier to see. GM studied failed motors, unused crankshafts, factory records, and reports from the road. Two faults kept returning: sediment inside rods and oil galleries, and crankshafts with the wrong size or surface finish. Both pointed back to supplier quality, not missed maintenance by owners, across thousands of engines built. Sediment inside an oil gallery can look harmless, but that passage feeds oil directly to the bearing surface. A small blockage cuts lubrication exactly where the rod and crankshaft carry their heaviest load. A rough or badly sized crankshaft adds another danger because the bearing must slide across that surface thousands of times every 1 minute without breaking the oil film. The scale was no longer small. GM counted 28,102 incidents tied to crankshafts, rods, or bearings. Among them were 14,332 reports of loss of propulsion, 12 crashes, 12 alleged injuries, and 42 fires. GM also said many of the fire causes were still unclear, but the pattern around engine failure kept growing across model years. The recall plan showed how serious the damage could become. Dealers were told to inspect engines, then repair or replace them when needed. Vehicles that passed inspection received higher viscosity oil, a new oil cap, a new filter, and an owner manual insert. GM was trying to protect the oil film itself. Soon, Toyota, Honda, and Hyundai would show the same weakness. Toyota's problem did not begin with a sudden failure. It began with machining debris left inside V35A engines. Under heavier loads, particles could reach a bearing, damage its surface, and change the engine. By May 2024, the result could be knocking, rough running, failure to start, or stalling. The link to GM and the crankshaft bearing was hard to miss. Toyota kept looking after the recall. Engineers collected engines from the road, opened them, studied the number 1 main bearings, and copied debris found inside. Bench tests checked whether the same damage would return. By May 2026, newer bearings showed the wear seen in the 2 earlier recalls. The problem followed the same path through Toyota and the V35A family. Honda reached the same ending from another direction. Some crank pins had been ground into a crown shape outside the correct limit. That small change placed extra stress on the connecting rod, bearing whenever the engine turned. Over time, the surface could wear, tighten, and seize. Inside Honda's V6, one shape error, bearing wear, and engine seizure became one continuous chain. The first Honda recall covered 248,999 vehicles, but reports did not stop. NHTSA later received 414 cases, while Honda supplied 2,598 more outside the recall. Regulators said those failures did not appear to come from the same crankshaft defect. The same part was failing again. That left the 3.5-liter V6 facing a problem the first recall had not answered. Hyundai had shown the danger earlier. Factory debris entered crankshaft oil passages, reduced lubrication, and heated rod bearings until knocking and failure followed. A separate 2025 recall revealed another route. Bolts with too little torque could loosen, damage the engine, puncture the block, and leak oil. Across Hyundai, Theta 2, and NHTSA, different mistakes kept reaching the same weak point. The piston, the rod, the crankshaft. 3 pieces working through 4 strokes, 3,000 revolutions per minute, 1 combustion cycle, and 1 spinning shaft. Fuel burns, pressure rises, and the piston is forced down. The rod carries that force into the crankshaft, which sends rotation toward the wheels. Heat, vibration, and changing loads never stop while the engine runs. Each part must return before the next explosion arrives. At highway speed, the same surfaces repeat that motion thousands of times every minute without being allowed to drag or lose shape. Between those metal parts sits something most drivers never see. A film of oil, thinner than paper, keeps 2 surfaces, 1 bearing shell, 1 oil passage, and thousands of rotations from touching directly. When the shapes are right and the oil stays clean, the crankshaft seems to float. Metal survives because oil stays between it under pressure for hours. The pump sends fresh oil through narrow oil galleries, while the spinning shaft pulls it around the bearing. Pressure alone is not enough. Clearance, surface finish, oil thickness, and flow must remain inside a small range for that protective layer to stay unbroken. The safe space is almost invisible. A journal shaped slightly wrong, a bearing pressed unevenly, or 1 hard particle can disturb it. Honda's crank pins, Toyota's debris, GM's surface finish, and 1 narrow clearance all reach the same place. Once the oil film breaks, the parts no longer glide. They begin scraping, heating, and wearing each other down each turn. The first contact may leave only a faint mark. The next rotation makes it deeper. Small pieces of bearing material can enter the oil, turning 1 damaged surface into contamination that reaches other passages and moving parts. Modern engines ask more from that tiny gap. More power, better fuel economy, higher pressure under load. Toyota's files showed how higher loads, bearing pressure, 1 trapped particle, and thousands of revolutions could turn a small defect into serious damage. Light driving might hide it. A hard pull, long climb, or heavy acceleration could bring it forward suddenly under load. The driver may feel nothing while cruising, then hear a knock when the engine is asked for more torque. Higher cylinder pressure pushes harder through the rod and into the bearing, exposing a weakness that stayed quiet for months. This is where Elon Musk's warning becomes easy to understand. An electric motor has no pistons, connecting rods, crankshaft galleries, or combustion bearings. It can still fail through software, cooling, wiring, or manufacturing. But this exact chain is gone. The motor creates rotation through magnetic force, without repeated explosions pushing metal parts against oil-supported bearings inside a hot engine block. That does not make every EV perfect, and it does not remove every reliability problem. It removes 1 long mechanical path where a tiny factory error can travel through oil, heat, friction, and load until the engine stops. The next question is how investigators proved these failures began in factories, not in owners' garages at all during normal driving. The knocking came first, then the oil light, then the smoke, the lost power, and engines that stopped without warning. 1 report could mean almost anything. But when NHTSA, vehicle owner questionnaires, early warning reporting, and warranty records began matching across the same model years, engines, and production dates, the road failures slowly pointed back toward the factory more clearly. The complaints were arriving from different drivers in different places, yet the sequence kept repeating. A warning sound, falling oil pressure, sudden loss of power. Once the same symptoms began appearing beside the same engine codes and build periods, individual breakdowns started forming 1 mechanical pattern. GM went deeper. Engineers opened failed engines, studied unused crankshafts, and compared both against field reports. The untouched parts mattered because road use had not changed their size or surface. By matching March 1st, 2021, May 31st, 2024, 6.2-litre L87 V8, and recall 25V274, GM narrowed the problem to a specific production window inside engines already sold to drivers. Sediment could be traced before mileage, maintenance, or driving style entered the picture. Crankshafts that had never turned inside an engine could still show the same dimensional and surface problems found in damaged units. That comparison made it harder to blame owners, oil changes, or unusual use. Toyota followed the metal. Failed engines returned from the road, while undamaged engines came in for comparison. Bearings were removed, measured, and placed under controlled tests. Engineers even pressed matching debris onto clean surfaces. By May 2026, Toyota V35A, number 1 main bearing, and recall 26V320 was showing the same wear seen in earlier recall groups under heavy loads again. The controlled testing mattered because it recreated the damage instead of only describing it afterward. When the same type of particle produced the same marks and wear pattern under pressure, the debris moved from a possible explanation to a repeatable cause inside the bearing system. Honda followed the factory timeline. Records showed when crankshaft equipment had been set incorrectly and which engines passed through during that period. But later failures appeared outside the first recall window. NHTSA did not force them into the old answer. It opened Investigation PE 25008, covering 1.41 million vehicles, after recall 23V751 and new Honda V6 failures kept appearing again. That widened the question beyond one group of engines. Investigators had to determine whether the original production mistake reached farther than Honda first believed, or whether a second crankshaft problem was creating similar bearing damage in vehicles that had never been included. Hyundai added something the others did not. Information from outside the company showed how the Theta 2 failures had been handled and how late some actions came. NHTSA's first whistleblower award followed. By then, Hyundai Theta 2, Kia 2020 NHTSA consent order and first whistleblower award had connected damaged engines, factory records, and delayed recalls. The pattern no longer looked random. Internal information helped show not only how the engines failed, but when the company understood the risk and how quickly it responded. The mechanical damage was serious. The delay made it larger because more vehicles remained on the road, while the same bearing and oil flow failures continued appearing. The factory errors were different, but the weakness was the same. GML87 carried sediment and crankshafts outside the limit. Toyota V35A carried machining debris. Honda V6 left with crank pins shaped incorrectly. Hyundai Theta 2 carried blocked oil passages and rod bolts tightened with too little force. 4 manufacturers, 4 mistakes, one system with almost no room for error. Each defect began at the factory, long before the driver heard anything. The engine could start, idle, and pull normally while a small piece of metal or one bad surface waited inside the rotating assembly. Oil decided how quickly those mistakes became damage. In recall 25V274, debris disturbed the bearing surface. In recall 24V381, particles reached Toyota's main bearings. Recall 23V751 traced Honda's wear to bad crank pin shape, while recall 15V568 followed restricted oil flow inside Hyundai engines. The defect only needed to weaken the oil film and let heat begin its work. That film is thinner than it looks, but it keeps the crankshaft from touching the bearing directly. Once pressure drops or debris cuts through it, the metal surfaces stop floating apart and begin scraping against each other. Every record moved toward the same place. The crankshaft kept turning. The connecting rods kept carrying combustion force. The main bearings and rod bearings had to survive pressure, vibration, and thousands of rotations. Loose bolts, rough surfaces, wrong shapes, or hard particles could disturb that balance. Different defects, same weak point. Once metal touched metal, the path towards seizure had started. Heat damaged the bearing coating, the clearance widened, and the knock grew louder. Oil could then carry more metal through the engine, spreading one local failure into a larger mechanical breakdown. Many vehicles drove normally for months or thousands of miles. Engines built from March 2021 through May 2024 could leave the factory with the defect inside. Recalls in 2025 and 2026 showed how long the damage could stay hidden. The driver heard the knock only after the bearing had worn enough to move badly, making affected engines difficult to identify early. Warning lights, rough running, or power loss often arrived after the internal surface had already been damaged. By then, an inspection might find metal in the oil, low oil pressure, or a crankshaft that could no longer turn freely. This is where Elon Musk fits into the warning. Tesla removed pistons, rods, oil galleries, valves, and combustion bearings. An electric motor can still fail, but not through this chain. Across 4 major recalls, one factory mistake could spread through oil, heat, friction, and motion until the engine stopped. Electric vehicles still carry their own risks through batteries, software, cooling systems, inverters, and high-voltage parts. Musk's point is narrower than saying every EV is safer. He removed one crowded mechanical path where a tiny manufacturing error can remain hidden for years, then destroy an engine in minutes. The next question is whether removing that chain creates a more reliable vehicle overall. 4 companies, 4 engines, 4 different factory mistakes. GM L87 carried sediment and crankshaft quality problems. Toyota 535 A faced machining debris and pressure around the main bearing. Honda 6 left some factories with crank pins ground into the wrong shape. Hyundai Theta 2 dealt with restricted oil flow. And later, rod bolts tightened below the correct force. No single supplier connects them. No one plant explains them. The link is the way different defects reach the same part of the engine. A recall also does not mean every vehicle will fail. Manufacturers draw a wider circle because the hidden defect cannot always be seen from outside. Some engines may carry debris, some may have a surface slightly out of shape, others may never develop damage at all. In several filings, Toyota used the required 1% estimate while also saying the real number was unknown. Recall 24V381 and Recall 26V320 covered broad groups because there was no clean way to identify every bad engine before it began knocking. Honda made the picture more complicated. After the original recall, rod bearing failures kept appearing outside the first production window. NHTSA said those later cases did not seem to come from the same crankshaft defect. That weakened the idea of one single cause, but it raised a harder question. The same bearing area was still failing through another route. PE 25008, 1.41 million vehicles, and Recall 23V751 left Honda with a second problem the first repair had not fully answered. Electric vehicles have their own weak points. Batteries can fail. Motors can fail. Software, wiring, cooling systems, and inverters can all create serious problems. Tesla is not free from engineering risk. Elon Musk made a narrower point. Remove the combustion engine, and you remove pistons, rods, oil galleries, valves, bearings, and the heat-loaded chain connecting them. Model S and Model 3 still depend on complex systems, but not on the exact failure path seen in these 4 recalls. Musk never released one report naming all 4 brands together. His role comes from the engineering direction that pushed Tesla toward a simpler powertrain. The brand-by-brand proof came from NHTSA filings, GM teardowns, Toyota bench tests, and Honda records. Different defects, same narrow margin. The final answer was never hidden in one secret part. It was hidden in a combustion system where shape, oil, torque, heat, and timing all had to remain right at the same time simultaneously. The damage did not begin at the fuel pump. It did not begin in the owner's driveway. It began much earlier, inside factories where a tiny piece of debris, a rough surface, a wrong measurement, or a loose bolt could leave with the engine before the driver heard a knock. Across GML 87, Toyota Fiat 35A, Honda V6, and Hyundai Theta 2, the pattern kept returning to the same place. Small production errors reaching the most heavily loaded parts inside the engine. A bearing can survive enormous pressure, but only when oil keeps the metal apart. The crankshaft turns, combustion keeps striking, and the bearing carries that force again and again. A bad surface can thin the oil film, debris can break it. Heat rises, metal wears away. The gap grows wider. The quiet engine begins to knock under hard acceleration or long highway climbs. Inside connecting rod bearings, main bearings, oil galleries, and crankshaft journals, one small defect can spread through the whole system. Once the surface is damaged, the repair becomes much larger than the original mistake. GM, Toyota, Honda, and Hyundai have all used inspection, repair, or complete engine replacement in response to these failures. A software update cannot rebuild worn metal. A new warning light cannot restore a scarred bearing because the damage is physical, not digital. Once the surface is gone, the damage is already inside. That is why a tiny factory error can end with an engine being removed completely. Hyundai tried to add another layer of protection through knock sensor software. The system could listen for unusual bearing noise, warn the driver, and reduce the chance of continued driving. But it only reacted after wear had already begun, during the final moments before seizure. It did not remove the connecting rod, the crankshaft, or the oil passage that made the failure possible. The warning could slow the final damage, but it could not erase the mechanical chain. This is where Elon Musk fits into the warning. Tesla did not solve every possible vehicle failure. Batteries, motors, cooling, and software can still go wrong, but the electric motor removed pistons, rods, oil-fed bearings, valves, seals, and crankshaft passages from the powertrain. Across 4 manufacturers and multiple recalls, the same lesson kept returning under normal driving, towing, or acceleration. Every extra moving part creates another place where heat, wear, torque, or contamination can travel until the engine stops. GM's record begins inside the 6.2-litre L87 V8. Sediment collected in rods and oil galleries, while some crankshafts left the supplier with the wrong dimensions or surface finish. The result was bearing damage, sudden engine failure, and possible loss of power across 597,630 vehicles. By recall 25V274, the weakness was no longer hidden inside one engine family. Toyota reached the same ending through machining debris. In the V35A engine, particles could move toward the main bearings, especially under heavier loads, and begin cutting the surface. Repeated recalls and the May 2026 teardown work found the same wear pattern in later engines. Recall 26V320, higher loads, and main bearing damage kept pointing in one direction. Honda's damage began with crank pins ground outside the correct shape. The connecting rod bearings wore, tightened, and could finally seize around the crankshaft. The first recall covered 248,999 vehicles, but the question grew when PE 25008 opened around 1.41 million more. Honda V6 recall 23V751, rod bearing failure, and NHTSA were now tied to a second unresolved path. Hyundai Theta 2 showed the whole chain most clearly. Factory debris restricted oil flow inside the engines. The bearings heated, wear accelerated, knocking began, and the engine could stall. Delayed action later brought NHTSA consent orders linked to more than 1.6 million vehicles and $210 million in penalties. Kia, the 2020 consent order, and NHTSA turned damage into a national warning. Different mistakes, the same crowded machine. Crankshafts, rods, bearings, oil passages, fasteners, and exact surface limits all had to survive heat and pressure together. One tiny error could travel through the whole engine. That is what Elon Musk had been warning about. Tesla removed that chain entirely. The final question is whether the combustion engine can keep gaining power without losing even more room for error against the electric motor on public roads.